So now we have an idea of how our data crosses the internet and how we specify or find the address for people that we want to talk to on the other side. But how do we actually send data to the other side? How much data do we put out there and how fast do we send it? We want to look at several key parts that are going to define performance and how we gauge how well our network is performing. So let's begin first by looking at the performance of the network. If you recall, we talked about the notion of nodes and links, where the node is an actual device that's going to either receive data or perhaps forward my packets. Each link then has a series of characteristics that are going to define our network. We care about these characteristics because they're going to define how fast our network or how well it's going to run. So to illustrate these properties, let's think about a pipe, where our data then are packets that are going to flow as water down this pipe. So the first property we want to look at is something called bandwidth, or our capacity of our link. Much like the height of a pipe or the diameter of a pipe is going to tell you how much water you can send down a pipe, we're going to do the same thing when we think about a network. We refer to this as bandwidth, and this frequently is going to be measured in bits per second. For most modern networks, we think about things in terms of megabits per second or even gigabits per second, which refers to the millions of bits or even billions of bits that we can send. And the capacity then is going to be a function of, for wireless, frequency, distance, and the amount of spectrum that we have available. The second property is delay, which can be thought of as the length of the pipe. The delay tells us how long it takes our packet to reach the node at the end of the pipe. Delay tends to be impacted by distance, as simple physics relates how fast the speed of light can travel. It takes a while for light to go from here to there. For many applications, we call delay by the term latency, and we measure it in milliseconds. We might refer to delay as the ping, or even go further and report delay in terms of something called round trip time, or RTT. And that refers to how long it takes my data to go from here to there and back again. On the wireless side, we will see that the type of wireless technology plays a key role in the delay in crossing a link. In its purest form, a network is just limited by bandwidth and delay for something in network that we call the bandwidth delay product. Generally speaking, the higher the BDP, the harder it is for the network to efficiently use it, and as bandwidth and delay go up, our work gets harder in terms of control. So speaking of challenges, most networks rarely exist in a pure theory form. The reality is we're not the only ones using the network. That means that while we can easily understand that the peak bandwidth of a link or its maximum capacity, we have the real world to think about, which means there are lots of other people jockeying for use of a particular link since we share it with lots of our friends. Plus, in addition, our packets are going to traverse many different links. At the end of the day, it's the smallest link or the bottleneck that's actually going to determine how fast we can go. And what happens is when those bottleneck links get overloaded, our packets start to get lost. The network just drops it because it can't handle it. We call that issue congestion. So much like we have protocols to tell us how to route packets across the internet, we also have protocols that help us correctly shepherd our data from one side of the internet to the other. For most applications, the dominant protocol is something called TCP, also known as the Transmission Control Protocol. TCP tries to deliver several key properties. First off, splitting up the network fairly, such that my capacity is shared equally. And then second, making sure to reliably deliver our packets. So even in the face of congestion or loss, our packets make it to the other side. TCP is used by both the server and the client, and it dictates all decisions on speed and retransmissions, and it's really what makes the network go. So while how TCP operates under the hood is a topic for well beyond this course, TCP tends to not work terribly well when we start to lose packets randomly. This frequently happens on wireless links, and it's often the source of frustrating wireless performance. The twist that wireless brings in is that we have to worry not only about congestion, where we might lose packets due to too many people using the link, but the actual link quality is going to change. So much like adverse weather might slow down highway traffic, signal quality on the wireless side is going to impact our maximum speed. Visually, we see this as the number of bars, or the signal strength, and what that is that maps the underlying RSSI, or received signal strength indicator, out from dBm, or the drop from initial strength, into something like 3, 4, or 5 bars.